In this next problem, number 5, you want to see that you really have the same form, limit as x approaches 0 of sine x over x. Although you're not going to, it's not limit as x approaches 0, it's limit as x approaches pi over 4. But when x goes to pi over 4, then x minus pi over 4 goes to 0, and you really have the same idea all over again. And this is just another hidden form of sine x over x. And the answer is 1, option D. We'll go on to problem 6. In problem 6, we're asked if f is the function defined by the following, for what values of x is f not continuous? The first thing you want to see is that each of these branches in and of themselves are always continuous. The only places we might have problems is where two different branches hopefully come together. If they don't, then the function will not be continuous there. So there are 3 places that we need to check. There are 4 branches, but 3 places we need to check. So the first one is sine of x from the left and x squared from the right at x equals 0. Now, sine of 0 is 0 and x squared at 0 is 0. So that one is fine. They both connect at x equals 0, y equals 0. Then at 1, from the left we have x squared, from the right we have 2 minus x. So we just plug in x equals 1. You get 1, and 2 minus x, you'd get 2 minus 1 is also 1. And so that one checks out at x equals 1. So now we just have to test the third branch, the third connection at x equals 2. So from the left it's 2 minus x, from the right it's x minus 3. We plug in x equals 2 into both of them. 2 minus 2 is 0, but 2 minus 3 is negative 1, and so that's not going to be continuous. So at 0 is continuous, at 1 it's continuous, but at 2 it's not continuous, and so that would be option C. And we'll go on to problem 7. Problem 7 is another limit at infinity, 3n cubed over n cubed, and so we're just going to divide the leading coefficients. So that's 3 over 1, which is 3. Pretty straightforward there. We'll go on to problem number 8. In 8, we're asked if the function f is continuous for all real numbers and f of x is x squared minus 4 over x plus 2 when x is not 2, then f of negative 2 has to be what? We know right away that x equals negative 2 is going to make the denominator 0. So what could we do if, assuming that that's a removable discontinuity, how can we redefine the function at x equals negative 2 to fill in that hole? So the way we're going to do that is by the limit. So the limit as x approaches negative 2, we're going to factor the numerator, x plus 4 times x minus 4 over x minus 4, and that leaves us with the limit as x approaches negative 2 of x plus 4. We plug in x equals negative 2 and we'd end up with 2. And that's the point that's missing. So we need to redefine f of negative 2 as positive 2, and that's option E. If we do that, that's the limit. If the value of the function is the same, then the function will be continuous there. We'll go on to problem 9. In this problem, we're told that y equals ax plus b over x plus c has a horizontal asymptote y equals 2. Well, recall you'll have a horizontal asymptote since the degree of the numerator and denominator are the same, and that means a over 1 is 2, so a is 2. If you have a vertical asymptote at x equals negative 3, then that must mean that the denominator is x plus 3. So c is equal to 3. So for example, y equals 2x plus b over x plus 3 has a horizontal asymptote of 2 and a vertical asymptote of negative 3, and the sum of a plus c is 5. Option E. We'll continue in the next video.